Welcome back. In this lecture, we will look at different forms of the phase diagram. So you will see this often. Okay. This all depends upon experimental convenience, whether you want to be measuring how the relationship between temperature and specific volume or pressure and specific volume. Okay, so it depends upon the kind of application and the kind of experiment you are trying to do. So you should not be memorizing these features. Okay, so you should build an intuition for sketching these phase diagrams. Okay, so that should be the approach towards all these things. So let's get started. So what we want to be plotting is looking at the relationship between temperature and specific volume, but at different pressures. Okay, we are going to be looking at the data for water, but this is fairly general. So one thing I would like to emphasize is both liquids and gases have continuous translation symmetry. Okay, so in some ways, they're fundamentally the same, and both are fluids, and they're different from solids, which have discrete translation symmetry. Liquids and gases have continuous translation symmetry. So because both of them have continuous translation symmetry, in some way they are the same, there exists a particular point in the phase diagram called critical temperature and pressure. So what are we plotting? On the y-axis, we have temperature, and along the x-axis, we have specific volume. So here it's specific volume is volume per unit mass, right? Meter cube per kg, and this you are plotting in centigrade, degree centigrade, all right? So what do we see? So this kind of a curve we have seen in a previous lecture. But what I would like to emphasize here is you're trying to look at the data at different pressure, in fact, at increasing pressures. So what does the data suggest? So this is at one particular pressure. If you look at this, that's what you've seen in the previous lecture. At low pressures, there is significant difference between a saturated liquid and saturated vapor. So I suppose you remember what is saturated liquid. So this is the point where beyond which, if you supply heat, vapor is going to appear. Okay. So what is saturated vapor? This is a point below which, if you remove heat, liquid is going to appear. Okay, so you have a system where constant pressure is maintained. So you have a subcooled liquid here. You keep on supplying heat to the system. The volume of the subcooled liquid keeps increasing to the point of saturated liquid. And then a two-phase regime develops. That's this point, this whole line. And that's where all the heat that is supplied doesn't give rise to increase in temperature. Okay, so all this is latent heat. Okay, the temperature remains a constant, and all the liquid gets converted to vapor. That is this point, right? So saturated vapor. So what do you observe? As the pressure increases, the difference between the specific volume of saturated liquid and saturated vapor decreases. So it keeps on, as you keep increasing the pressure, there is a point called the critical point where the volume of the saturated liquid and the volume of saturated vapor is the same. All right. So beyond this, you cannot differentiate between saturated liquid and saturated vapor. So this is really possible because of a fundamental reason. The structure, both the structure of liquid and gases have continuous translation symmetry. Okay, so that's the important reason why you introduce these terms called continuous translation symmetry and so on. Okay, so this kind of behavior won't be there when you're looking at solid to liquid transition. So that's what it is. So you have to develop an intuition for plotting these things. Once you first imagine how this experiment is conducted, you have a natural intuition for this, and then you can sketch this. The only thing is this point of critical point. Okay? That is the only concept which is sort of introduced here. So what are we plotting here? So we were just elaborating on the same point in some ways. So here, so we have plotting for, this is the critical point. So just if you contrast, so we are joining all these points. Okay, this is called a dome, we call the two-phase dome. All these points are joined together, and the two-phase region, liquid and vapor region, exists here. Beyond this dome, there is no two-phase region. Okay, so in this we call as the compressed liquid region, okay, or the subcooled liquid region. So here you have the superheated vapor, right? So if we keep heating the vapor beyond saturated vapor point, just the volume of the liquid increases. So that's what we are trying to plot. Okay, so all this one particular line is at a constant pressure. This is at an increasing pressure. So this two-phase region, the difference between the volume of saturated liquid and saturated vapor exists till the critical point. Beyond this, you cannot differentiate. So that's what is also shown here. So there's a phase change that is here. That phase change is possible between liquid to vapor is possible if you are at pressures that is below the critical pressure, right? So this critical point for a particular liquid, you have critical temperature and critical pressure, right? So both are in a way related. Okay, so we will see why these are related and so on. So we can also define something called a critical volume at that critical point. Okay, so these are all just additional terms. Okay, so it doesn't add much to the concept. So it is this whole thing about critical point and a solvent existing above the critical point is very important. It has very important applications in chemical engineering and as well as in chemistry. Okay, so these supercritical solvents are very important for supercritical extraction. Sometimes you extract perfumes, okay, and using supercritical solvents, and they are also important reaction medium, okay, for certain kinds of reaction, which are better done with supercritical solvent. Why is that? So typically liquids offer greater solubility. Okay, sometimes you can dissolve certain components in liquid better because there is more interactions, right? Because of that reason, supercritical liquids are better medium for offer greater solubility. Okay, however, mass transfer movement is of the component which you have dissolved is very difficult in a liquid, but the component can move more easily in a gas, right? So in some ways, you can think that supercritical solvents bring in best of both worlds. They offer a medium where the solubility is like a liquid, whereas the dynamics, the movement, okay, diffusion and so on, self-diffusivity and so on, is more similar to what you may see in a gas. Okay, that's one of the way to rationalize why supercritical solvents are used in chemical engineering and in applied chemistry. We'll move on. Okay, so again, so there is a general intuition of as temperature increases, specific volume increases, right? So you put in more energy into the system. If you, like, for example, in a gas, okay, you would think that the specific volume is going to increase. So as the pressure increases, you would also think the specific volume is going to decrease, right? So with this intuition is good enough to convert these two phase diagrams. So I'll mention. So here, what are we plotting? Temperature is on the y-axis, specific volume is on the x-axis, right? So if you want to plot pressure on the y-axis, specific volume on the x-axis, but plotted at different temperatures as opposed to different pressures. Okay, you should be able to plot. Okay, so what is the general intuition? Corresponding to this, as temperature increases, specific volume increases, right? So you can see, right? So pressure is kept a constant. You're increasing the temperature, the specific volume increases. This is the two-phase region. And again, the specific volume keeps increasing as the temperature is increasing. You're supplying heat to the system. So with this intuition, before you look at the graph, you try to sketch for yourself how, if you plot pressure in the y-axis, specific volume in the x-axis at different temperatures, what is going to happen, right? So this is going. I mean, you can again. This just fits into this particular notion, right? As pressure increases, specific volume decreases. That's all you're trying to say, right? As the pressure increases, right? Pressure is increasing in this direction. The specific volume is decreasing, right? And all the rest are the same, right? So it doesn't. See, we conducted when we did this experiment. We showed how this experiment was done. We did this at the piston. There was a constant pressure that was applied to the closed container. Okay, so there was a lid, piston lid, which was moving, but there was a constant superincumbent pressure. So you can also conduct a different kind of an experiment where temperature is kept a constant, but pressure is varied. Okay, so that is, if you put enough different kinds of weights on top of the lid, and if you keep removing the weights, you are changing the pressure, right? If you add more and more weight to the system, you are increasing the pressure. If you remove the weight, you are decreasing the pressure, right? So that's all that is to it. Okay, so this is something which you should not be memorizing, but you should be able to draw all these diagrams by some general intuition you already have, right? So I will end this lecture here. Thank you.